now let's take a look at example number 4. We want to consider the following questions that are related to example number 3. However, in this example, we're going to note that the interval of time is going to change in each one of these different parts. This is kind of an important thing to be able to account for. What happens if that interval of time is adjusted? So let's see. What is the probability that there will be at least 2 accidents, not during the next week, but during the next 2 weeks? What this shows us immediately is that we can't use the same variable that we had up here, because this was the variable of x, which represented the number of accidents that happened within a week. What we're going to have to do is redefine our variable rather quickly. Let's suppose here that x represents the number of accidents that occur within the next 2 weeks. Well, I can still see that here x has a Poisson distribution, but this is a different x than before. The other thing that I'll notice now is that my lambda is going to ultimately have to change a little bit. Notice that since I'm working with a lambda value before of 1.4, that was 1.4 accidents per week, I now need to figure out what would be the average number of accidents to occur in 2 weeks. Now this typically isn't difficult. I can see that if lambda was 1.4 for 1 week, I should be able to say that I want 1.4 times 2, because I have 2 weeks worth of accidents. So I would have 2.8, and this would be accidents per 2 weeks. Now that I have my new updated lambda, which is always really what's going to change when I change my interval of time, I now know that I want the probability that x is, again, at least 2, so that's going to be greater than or equal to 2. Now, if again I'm thinking about my table of possible values over here, I can see that the number of accidents that might occur could be 0, 1, 2, 3, 4, on and on and on. And I'm interested in grabbing the values that occur from 2 and up. It's difficult to get those values, at least directly. So I'm going to try to tackle this with a 1 minus approach. I could do 1 minus the only percentages that I don't want, which would be the probabilities for x being less than or equal to 1. Notice this would be 1 minus a Poisson CDF with 2.8 average per 2 weeks and comma 1. Now once I have this, I can go to my calculator and crunch all this out in one line. So once here, I would just click 1 minus, then I go to my second command, my vars button. I'd go through and find my Poisson CDF. I'd plug in 2.8 and now the value of 1. So this is what I had written down on the page and also what I've typed into the calculator. And I get my final answer here of 0.7689. So my final answer of 0.7689. Notice that on each one of these subsequent parts, I'm going to have to continue to kind of change up what my lambda value is going to be based on what's going to be happening with my change in the interval of time. Take a look at the changes that we're going to be in for in the next couple questions. What is the probability that there will be exactly 5 accidents during the next 4 weeks? What about the number of accidents that occur tomorrow? The interval of time is continuing to change. So I could even see down here on part D, what is the probability that there will be no accidents in the next 3 days? So I'm going to ask you right now to go ahead, pause the video, see if you can work through these questions. Be sure that each time you're going to define your random variable, and then you'll be able to state what the value of lambda is, and then set up your calculation. When you hit unpause, you'll see me go through the solutions. Okay, so we have all the answers up here on the screen, but I'll walk through each of them individually. For part B, we were dealing with the next 4 weeks. So we had our variable represent the number of accidents that occur within the next 4 weeks. We had to take our original lambda, which was for 1 week, and quadruple it. You could have also taken the previous value of 2.8 and just doubled it, but either way you get 5.6 accidents average in 4 weeks. So since I wanted exactly 5 accidents, I set up a Poisson PDF with 5.6 and 5, and I got a final answer of 0.1697. For part C, I wanted the probability that there would be 2 accidents occurring tomorrow. So X would represent the number of accidents that occur within 1 day. Now, if 1.4 was the original value of lambda that stood for the number of accidents in a week, I could divide that by 7 to figure out the number of accidents per day, which is 0.2 accidents per day. So I set that up in a Poisson PDF with 0.2, 2, since I want exactly 2 accidents. And I get a final answer of 0.0164. Finally, for part D, I see here that I want to let X represent the number of accidents that occur within 3 days, since I'm interested in having no accidents in 3 days. Lambda, again, was originally 1.4, and that was accidents per week. If I divide by 7, I get accidents per day, and if I triple it, I get accidents per 3 days. So you can see here I have a lot of playing around that I can do with in order to get the value of lambda that I need. But once I had that, I was able to set up a Poisson PDF again with 0.6 and 0, and got a final answer of 0.5488. Now the last question that we have here is part E. You probably didn't take a look at that yet since I only asked you to go through part D. Let's see what we have here. This one asks, what is the probability that there will be exactly 2 accident-free weeks during the next 4 weeks? Oh boy. Well, this is kind of strange. Notice here that I have something kind of interesting taking place. I want 2 of something out of the next 4 of something. So I want 2 accident-free weeks out of the next 4 weeks that we have. Does that remind you of any other distribution that we've talked about? Yeah, that kind of almost sounds like a binomial distribution. Remember, a binomial distribution always asked for a number of successes in a fixed number of trials. So this is interesting. I have a completely different variable here. I'm going to go ahead and say, how about we let y represent the number of accident-free weeks. Y will represent the number of accident-free weeks in the next 4 weeks. Notice that now when I say in the next 4 weeks, that's not really like a unit of time, right? Because I'm treating each week like it's an item. And I'm saying, is the first week accident-free? Yes or no. Is the next week accident-free? Yes or no. Well, again, I should be able to go back to my formula sheet and just quickly double check, is this actually a binomial distribution? Do I have a fixed number of things I'm going to go look at? Well, yeah, I have 4 weeks worth of 4 weeks worth of time I'm going to go look at here, 4 individual separate weeks. I could also then say, well, every week is either accident-free or it's not. We were already told that what happens in one week and the next week are independent. We were told that all the way back up in the original problem. And the last thing we would need is our chances of success. Well, I think we can find that, but it's going to take a little bit of time. Let's see what we have here. I'll say that y has a binomial distribution. I can kind of hear the rhythm of that binomial in there. Number of successes out of a fixed number of tries. But remember that when I'm working with the binomial distribution, I need to have a value of n, and I need to have a value of p. Well, to find my value of n, that's easy. I already have that. That's the value of 4. However, if I wanted to go ahead and actually find my value of p, that's going to take a little bit more work. My value of p is unknown right now. All I know about my value of p is this. I could state that to find p, we need to know the chances of having an accident-free week, right? Because that's what I would need to happen to get a success. So what are the chances of having an accident-free week? Well, wait a minute. That would mean that I would want 0 accidents to occur within 1 week of time. Oh gosh, here's where things start to get confusing. While the main overall question here is binomial, how many accident-free weeks do you get out of 4 weeks? This question down here is Poisson. Notice down here, I could say X represents the number of accidents that occur within 1 week. And so here I could see that X has a Poisson distribution. I kind of have a Poisson distribution inside of a binomial distribution. This is very strange, but I can see why I need it. How do I know that I'm going to have an accident-free week or no accidents in 1 week? That's exactly what a Poisson distribution would ask for. And so I would need to know the value of lambda. How many accidents do I expect there to be within 1 week? Well, this problem already said it was 1.4 accidents per week. So to find that value of p that I needed up here, I could do that by calculating the probability that the number of accidents that there are in 1 week worth of time is 0, accident-free. And so I would do that by calculating a Poisson PDF with lambda being 1.4 and my x value being 0. If I switch over to my calculator, I can see how I would compute this. I would come over here, I would click second, vars button, I would go to Poisson PDF, 1.4 with a 0, and there it is, 0.2466. So on here, I'd be able to go ahead and write down 0.2466. Okay, great. So now that I know what the value of p is, again, I've just done all this work to find this value for p. Now I can actually go ahead and answer the binomial question. So the probability that y, the number of accident-free weeks, is going to be 2. That is a question that is binomial in nature. So I'm going to say I'm going to need a binom PDF. Out of 4 weeks I'm going to look at, there's a 24.66% chance, let me rewrite that to make it a bit cleaner, but there's a 24.66% chance of getting an accident-free week, and I want 2 of the 4 weeks to be accident-free. Again, if I go back to my calculator, I can easily go ahead and compute this. I'm going to go do my binom PDF 4.2466 with 2 in there. That's what I already had typed into the calculator. And there's my final answer, 0.2071. 0.2071. So this is even kind of a step above what we saw back in the geometric distribution a few examples back. It's important for us to recognize now, not only can some of these columns be intermixed in the same problem, and that is in terms of like part A might be geometric, part B might be binomial, part C could be Poisson, but now I also have to be careful of kind of hybrid questions, where maybe in order to find this p-value in the binomial, I need to go ahead and actually use something like a Poisson distribution in order to help address that. So these questions can be a bit overwhelming at first, and you might have a lot of questions on this example specifically. And if you do, don't hesitate, don't put that off. Feel free to contact me and ask as many questions as you can possibly come up with to make sure that you understand this idea. And of course, problems in the worksheets will help you to address these questions as well.